Good afternoon. Good afternoon. Welcome
Good
to our,
afternoon.
to our third day of training. I think maybe we wait for about 2 minutes to allow others to join in. And also, as my colleague gives you rights to the course.
It's okay.
Yeah, Dr. Pio, I think you can start.
Thank you very much, everyone. Good morning, evening, good afternoon, whenever you are. Welcome to our fourth day of our series. Before Peace comes in, I would like you to know that what we are going to be covered in 5 days, it takes 2 semesters to cover. So if we go a little bit faster, please forgive us because we'd like to cover as much as possible. Okay, Peace, you can start. Thank you.
Thank you, Stephen, and thank you all for joining. Good morning, good evening, good afternoon, wherever you are. You are welcome to the 4th day of our training series. We are going to continue from where we stopped yesterday. But as we did yesterday, we are going to go to the Google Drive and we get material that we are going to use today. So we have quite a lot of material that you're going to use today. So we will be picking them. We will be picking them from the Google Drive. So I'm sharing my screen. So let me know if you can see my screen. Okay, yes. So great. Now, in the Google Drive, for this particular session, we should download this R script here, logistic regression. Logistic regression. So please download this one and put it in your folder. The codes that we are going to use today are for logistic regression. Yesterday, we looked at this code for linear logistic regression. Today, we'll look at the code for logistic regression. Another thing that you need to do today, we will be introducing QGIS and using it during the session. So if you have not installed QGIS, look for the file that contains the installation instructions, which is this one here, install_QGIS, and download QGIS according to the instructions. Click on the link inside that document. So we will use QGIS as we go along today. Make sure that you start downloading it if you have not downloaded. Install it if you have not yet installed it. And so also we shall use the data sets that we used yesterday. There are other files that you will download from this Google Drive as we go along with the sessions. All right, so if you have downloaded the logistic regression file, then come to R and open that file. So if the file is within your directory, you can just come to File. Because this is an R script, you can come to File and then go to Open File. Then in your data science, if that is where you put it, you will look for it. Mine is here, logistic regression, open it. It should open in your script editor. So this is what you want to see in your script editor, the logistic regression R file for today. And we'll see the data sets that we are using. They're not new. We are using the data set of yesterday. That's the crop recommendation data and the Kenya data. So if you have them, that is great. If you don't have them, you're going to have to import them. Okay. Somebody's saying we explained how to access the file. If you have downloaded the file, then come to File here and click on Open File. Okay, so we are not importing this file because this is not a data set. We import data sets into our environment, but we open files, especially scripts that have a file extension of .r. Those are files that need to be opened from the menu here. So go to File, click on Open File, and if you've put it in your data science folder, you should be able to find it. Click on it and open it. The other alternative is to go direct to your folder, double click on the logistic regression. You will be able to have it open here. All right, so is this a new file different from yesterday? Yes, new and different from yesterday. So if we ask you to download, it's because there is more information for the session that we are going to use today. All right, if you've succeeded, let me know in the chat. Type 1 if you've succeeded in opening the logistic regression folder. Somebody's asking for the link to the Google Drive, I suppose. Okay. So the link is going to be shared. The link is right there. Click on the link, go to the Google Drive, download the logistic regression R script. Open it up. We need to have it here. What about the software to download? The software is not in a folder. The software in the Google Drive here is this file here, install_QGIS. This is what we are going to install. So you can download and open it. Make sure that you install QGIS as we go along because we need it during the session today. Okay. If we've all succeeded, that is great. Now we start our session today, and we are starting our session today by looking at our PowerPoint to guide our discussion. Yesterday, we concluded our session by looking at linear regression models. Now, we said there are so many models in data science that help us to do predictive analytics. We are under predictive analytics. So the first model that we looked at was the linear regression model. And we saw that the linear regression model specifically helps us to predict numerical outcomes, okay? But it is not always the case that we are dealing with numerical outcomes. Sometimes we have problems that require us to classify information into preferred groups or existing groups. For example, in our case, we have information about farms and crops, and we want to classify and see if we can predict whether the yield will be high or will be low, okay? So this kind of problem will require a different model compared to the linear regression model. So the type of problem that we have is known as a classification problem. We want to be able to classify our outcome into two groups. One can either be high or one can be low. This is for the yield that we have. Remember, we already have a data set for the crop recommendation. That data set already contains information that was collected, and that is the information that we use to create a model, an appropriate model that helps us to do predictions. So you can also do predictions with classified data of this nature. And it is very common to actually have this kind of information instead of variables that are linear or variables that are numeric in nature, hence require the linear regression model. So today I introduced the logistic regression model. The logistic regression model is a model that helps us to solve classification problems. As I said earlier, this helps us to be able to classify information into groups that are known, groups that we already know. So what you need is to check whether your output will fall in either one group or another group. You can have many groups here. In our case, we have only two. You can have many groups here, and you can still be able to use the logistic regression to classify, but also to predict the group in which a certain outcome will fall, okay? Now, the logistic regression model is applicable to not only the agricultural field, it is also applicable in different sectors, in the health sector. You can use it in finance, you can detect fraud, okay? You can detect disease, you can detect risks, etc. So it is a model that helps us to do anything that requires classification. So it predicts the probability of a binary outcome. So the outcome variable has to be a categorical variable. In our case, we have one that has two categories. So if you have variables that are captured as yes, no, died, alive, high, low, fraudulent, not fraudulent, you know, all those will require you to use something like the logistic regression model. Meanwhile, the logistic regression model is not the only model that classifies. We have other classification models that we are going to look at today as well. So the logistic regression model specifies relationships between X and Y. Yesterday, we said that in a linear regression model, the relationship between X and Y is linear. So ideally, there is a straight line that specifies the relationship between X and Y, where you can predict, for example, the slope of that line. But now, when we are looking at logistic regression model, the relationship between the outcome, which is Y and X, is not specified by a straight line. It is rather specified by a sigmoid curve, and that is the curve that we use for prediction. So when you have information and you want to predict classes, groups, you can consider using the logistic regression model. So how does the logistic regression model work? You need to know. When you have your outcome, like our yield has only 2 possible categories, then you use the binomial logistic regression. So this is more of the binary one. But if the classes are many, you can use multinomial logistic regression. We can run these as well. And if those many classes are ordered by a certain nature, like levels of education, here we have an example of a rating like low, medium, high, then you can choose to use what we call the ordinal logistic regression. So in our case today, we will start with the simplest, which is the binomial logistic regression, in which we have 2 possible outcomes. That is predicting high yield, either it is high or low. So when you run the logistic regression model, you have outcome. We are going to practically do this to see if you can also do the same. The data that you have already has information about high yield. And this information, yesterday we said, is what is collected for us to be able to use to predict. And you predict basing on data that has been collected. You can use the entire data set like we did to create the model, train the model, but also you can use the entire data set to do prediction. Another way, which we're going to see, is to split this data into a certain ratio. It can be 70% to 30%. Then you use part of the data to create the model, and then you use another section to evaluate the model. Then you do predictions. Then you use the model for prediction. So when you use the logistic regression, what you're predicting now is not a value like that in the linear regression. You are predicting a class, okay, or a category basing on the model that has been established to check the relationship between Y and X, and hence use it for prediction. So it means that depending on how the model is performing, you can have a prediction that is a bit different from what is given or what you observe. Just like yesterday, we were predicting the milk yield. And so some of the predictions, if not most, were not exactly equal to the milk yield. So if you have a milk yield of like 420 liters, your prediction or your model can give you 423. So there's a margin of error that is associated with these models, and you evaluate the model to see how good it performs. Better models are more likely to predict with better accuracy, okay, as we are going to see. Now, so the logistic regression model then will predict the class. So if it predicts the yield to be high when it was originally high, you will find this under the predicted values. But sometimes, depending on how it's performing, the yield can actually be low, and the prediction classifies it as high. And it uses a probability to do that classification. So it also means that you can predict a yield to be high when in actual sense it is actually low. You can predict it to be low when it is high. You can predict it to be high when it's actually high. And then you can predict it, for example, to be low when it's actually low. So good models help us to predict. So if you have a good model specified, trained in the right way, you should be able to do these predictions here. So that is how the logistic regression model works, okay? So the logistic regression model can also take many variables to try and explain the classes that you have so that you can have better prediction. You can also have only one variable. For example, the feed intake. You could use only the feed intake to predict whether the yield will be, for example, high or low. But as we see, when you add more variables into the model, you tend to have better models that predict with better accuracy. So we are going to go right into R so that we can run our logistic regression model. If you already have opened the logistic regression, we are here. So good practice, we load the libraries that we are using. So where you see the libraries, just load all of them. You never know when you need the function that comes from that library. Highlight and run, or just put your cursor there and run. Please run them. Make sure you see activity down here in your console to see and show that you have successfully executed that line of code. The other important thing is that before you start running, manipulating data, make sure that the data is actually imported into the R workspace. And we are using the same data sets that we used yesterday, specifically the crop recommendation data. You can import it through this code. You can also import it if you don't have it. I mean, I'm just overwriting it, but I do have them already existing here. I have quite a number of other data sets also, but I am interested in the crop recommendation data. We also have the animal data that we are also going to use. So actually import all of them if you don't have them, the animal data, the crop recommendation data, the Kenya data, we have where we're going to use them. The data sets have not changed. So if you have them from yesterday, then confirm so that we can have them together. If you are unable to import data from the script, come to File, here, Import. If we are dealing with a CSV file, import from readr. If we are dealing with an Excel file, import from read Excel. Okay, for example, the animal data is a CSV file, so we import it from readr. Okay, the crop recommendation data is an Excel file, so you import it from Excel here. All right, so it's important that you have the data. So if you have the data, then we proceed. If you don't have data, let me know. If you cannot see your data in your environment, if you've succeeded, yes. If you've succeeded, just type there, yes. If you're looking for the material for the training, please find it in the Google Drive. Find the link in the Google Drive. You will be able to access everything. All right, that's great. So together, let us proceed. And we are starting with logistic regression. And the logistic regression that we are going to do, we are going to predict yield. We are starting with the animal data. Make sure you have your animal data and it looks like this. It has the yield variable here, classified as high or low. Make sure you can see that one. So for logistic regression, we need our outcome variable that we are going to feed into the model to be specified as 1, 0, where 1 represents the outcome of interest. In this animal data set here, we are interested in especially the high yield. So the line of code that does that, line 11, should create the outcome variable where 1 represents high and 0 represents low. Okay, so if we run this line of code successfully, the number of variables should increase. Specifically, you should see the outcome variable created here as 1, 0. Okay, that is what that line of code does. Yes, if you have seen your outcome variable, confirm if you have run that script successfully, because we cannot run the models if we do not see the outcome variable now at this point. All right, so that's great. Okay, so we have it. So the GLM model is the one that is going to help us to get the logistic regression model. We just have to specify the link as logit. And so run the logistic regression model and summarize the model as well. Okay, so you should be able to see a summary of the model here, also indicating if that predictor variable is significant in predicting the class. So in our case, our model has only one predictor variable. I've just started with one, this one here. So we are using the body weight, this one, to predict the outcome, okay? And we are going to be able to classify basing on the strength of that model. So make sure that when you summarize, you can see the predictor variable right here. The stars represent the level of significance in relation to predicting the probability of belonging to one class versus another. And when you run a summary, do the prediction as well using the predict function, okay? And specify whether it is high or low, and that is what we are doing. So
yes, I got somebody saying your voice is very low. I wonder whether the rest are hearing you. We can ask them.
all right, can you hear me clearly today? Okay, it seems they can hear me. It seems they can hear me. Okay, all right. Okay. All right, so I think somebody may need to check. Let me check my volume. All right, so we can proceed. We can proceed. So when you do the prediction, you can check in the data set now. If you've run your prediction, you should check and see your prediction outcome there. Okay, so run. When you run, you can verify and you will have your prediction. So this is what I want you to see. I want you to see the predicted class for each animal or for each farm. I would like you to check and see whether you are able to predict basing on the regression model that you have just created. The original data is here, classified as high, low, high, high, high. Our prediction is here. So you can see that sometimes the prediction does not match with the original data set, but that also depends on how the model is performing. In our case, we may say that we are unable to capture some of the classes correctly because we are only using one variable to try to predict the outcome. So we are now going to increase the number of variables into our data set or into our model, use more information to see if it improves on the probability of predicting that outcome. All right, somebody said we are fast, so somebody is saying unexpected symbol in logistic regression. Did you run the library? You are not seeing the prediction class. Which data are we using? Okay, so if you're able to see, please specify. I will repeat the data we are using. If you we are using, we are here. So I'm trying to read the comments just to understand the challenges that you're getting. So if you've succeeded to see your predictions, please confirm. All right, log mode not found. So the problem is you did not run the libraries. So let's go back. So for all of us, make sure that you have the animal data. This is the data set we are using, this one. So just make sure everybody has their data. If you don't have data, go to import under environment here, import this data set. I think it's a CSV file. Browse and find it wherever it is. Open and import. Okay? Open and import. You should be able to see it there. And then when you import the data, run all the libraries. Okay? Run all the libraries because you might not be able to use the functions if you don't run the libraries. And then after, perform the regression from line 9 up to, you can run up to line 24. Okay, so this one just gives you a snapshot of the predicted class and the original classification. So you can run up to line 24 so that you can see a snapshot of what is being predicted. So that is where we had stopped. And that is why right, so I'm just trying to read here. Animal data not found. If your animal data is not found, it means you did not import the data set. It means you did not import the data. So please import the data set. Make sure you can see the animal data here in the environment. This one here. Make sure you can see it. Make sure you can see it. And if you're not finding the function, it also means you did not run all code and load the libraries. Okay, so I see there are people who have succeeded. There are people who have succeeded. Type 1 when you see your predicted values. Okay, so now I see that we have them. All right, that's great. Okay. All right, that's perfect. So we can proceed. The last thing we are doing is that we are going to simply add other predictors onto our data set and also into the model. So you can see that this other model here, the GLM model which we are using, now contains more predictor variables compared to the first one. So we have added all the variables that we think can help us to predict the class correctly. So I would like you to run from where you have logistic regression with many predictors up to the end of the code in order for us to see if we improve anything with our prediction. To see if we improve anything. So this is better than the previous one. At least we are able to capture high, 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 low, low, high. You can run and see if you are able to do a prediction for the new model that contains more predictor variables. For the new model that contains more predictor variables, you can type yes if you succeed. You can also just put a snapshot of the outcome. Okay. How come mine isn't rounding off? Somebody has errors as well. Okay. Looks like we are succeeding. Okay. It looks like we are succeeding. Put the outcome there. Put the outcome there. Cannot subset columns. If you cannot subset columns, it's because you did not run the libraries. Run the libraries that are up. When you are using the code, if you don't run the libraries, there are functions that don't work. It's important that you have them loaded every time you do that. Okay, so it looks like I'm seeing people able to do the prediction. People are able to do the prediction. Now, we can also determine how much of this has been predicted correctly, okay? And that is done when you are evaluating the performance of the model. Somebody says they're lost. Where exactly did we lose you? Are you able to run? Are you seeing the predictions on your side? Somebody is unable to see the animal data. Did you run the libraries? Did you? Somebody is asking, how do you know the cutoff? The cutoff is 0.5. The cutoff is 0.5. The cutoff is 0. The cutoff is 0.5. Somebody's outcome looks different. Can you paste your outcome there so that we can see? We are not installing anything else today. Okay, so somebody's saying share the libraries. The libraries are here in this code. We have libraries here. We have the libraries up here. Just run them. Click on run so we can be able to see them. All right, so we are going to look at these models. We are going to evaluate these models in a short while. We are going to evaluate the models in a short while. Somebody is saying they want an interpretation of the code. So one, we can explain this code. So the logistic regression itself is run using this particular line of code. The log_mod is just a name of the object that's going to contain the output. Okay, GLM is the function that produces the actual model. And within the GLM function, you specify the outcome variable, which in our case is outcome or Y. And then after you specify all the predictors by adding them in the way we did with the linear regression model. And at the end, you need to specify the data set that you're using, which is the animal data. And then you also specify the link as logit so that you can produce the logistic regression model. After that, you do a summary so that you can see the output of that model. And then the predict function, this one here, is the one that helps us to do the prediction. It produces the probability of belonging either to the high class or to the low class. And that probability should appear in your data set once you do the prediction. It's here. Now, this probability here actually is the probability of belonging either to the high class or to the low class. And the cutoff of this probability for you to belong to the high class is 0.5. So you will also note that where it is above 0.5 or 0.5 and above, the classification, the predicted class is high. Where it is below, where the probability is below 0.5, the prediction is low. So it depends on the probability that has been generated and computed to place the prediction either in the high class or the low class. The prediction is not ambiguous, okay? It actually depends on the probabilities that have been computed of either belonging to the class of interest or not belonging to the class of interest. If the probability of belonging to the class of interest is high, which is 0.5 and above, then you are placed in the high class. If it is low, which is below 0.5, then you are placed in the low class. So in the end, we want to be able to understand how we are doing the prediction. How do we specify the cutoff number? We specify the cutoff number. One, the cutoff number is known, but we also specify it using the if-else function here, so that if you are high, if you're beyond 0.5, you are high, or otherwise you are put in the low class. You are put in the low class. So basically, this is what happens. So we don't determine what will be our cutoff number. Our cutoff number is 0.5. The probability ranges from 0 to 1. So the cutoff is right in the middle there, 0.5. So it's computed, and it's used to place you in the appropriate group. Now, let's proceed. We are going to look at how to evaluate these models after this. So for now, I would like to introduce a concept called machine learning. We've heard of machine learning before. We need to understand what machine learning is so that as we proceed, we quickly understand what machine learning is and what we are doing with machine learning algorithms, because we've already started using them, but sometimes we confuse machine learning, what it is and what it's not. So machine learning is what allows computers to learn and make decisions without being explicitly programmed. What does that mean? It means that when you specify an algorithm, okay, that the model or the computer uses to do predictions, it will continue to use it. When you add data, it will continue to learn from that data, and it will continue to make the model better and make better predictions over time. So it involves feeding data into different algorithms that help us to identify patterns and make predictions on new data. Now, for us, we've made predictions on the data that we have, but you see that model, when we deploy it to tomorrow, for example, you can use it to make predictions when you have a new set of data, okay? So this kind of approach helps in different fields. You can use it for image recognition. You can use it for speech processing, language translation, recommender systems, etc. Now, the process of machine learning is essentially the process of modeling, which we have already looked at. So it's important that you understand the process, okay? One, we need data, which we already have. We need to train the machine by running the models on the data sets using the appropriate algorithms, okay? And then we build the model and then we predict the outcome. Now, we have already done a machine learning process by specifying either a linear regression or a logistic regression and being able to produce or predict the outcome variable. Whether you are producing or predicting a linear outcome or you are producing or predicting a classification outcome, the whole process ends in prediction because that is the ultimate aim of modeling. Okay. Now, in R, machine learning works in such a way that you need to take the steps that we have already taken. So I am taking us through steps that we have already taken, and so that you know that what we have been doing is already machine learning. 1, clean the data using packages like tidyverse and dplyr. We have already done this. So the selection of data, the transforming of the outcome variable is what we call data cleaning. If you have missing data, you check for them. If you're looking at outliers, you check for them. Now that is what data cleaning is all about. So it's more like doing exploratory analysis as well. Then select the algorithm. There are many algorithms that we can use. We have so far looked at 2. One algorithm is linear regression modeling. The second algorithm is logistic regression modeling. We've looked at them. And you choose the algorithm according to the problem that you are tackling. Now, because we had an outcome that was linear in nature, we chose the linear regression. When we had an outcome that was categorical and we wanted to do a prediction of a class or a group, we chose the logistic regression. So choose the right algorithm to perform the task. If you choose the wrong algorithm, the machine will work. The model will be working. Sometimes it works, sometimes it doesn't, but it can give you wrong output and wrong predictions if you don't choose the right algorithm. Then we train the model. We use the different functions that exist for us that help us to run these models correctly. For example, we use the LM function to create a linear regression model. Today, we have used the GLM, the generalized linear models, to come up with a logistic regression. There are other functions also that help us to do the prediction, which we have already done today and yesterday. The predict function in particular is the one that helps us to predict the outcome. What we haven't done, which we are going to do today, is evaluation of the model. You evaluate the model basing on certain metrics like the R squared to see which one might perform better than the other. So this is how machine learning works. So whatever we've been doing as we are trying to predict information or to predict our outcome is already machine learning. That is what we refer to as machine learning in data science. So in agriculture, there are many applications of machine learning, not just in agriculture, but in different sectors. But today we shall concentrate on agriculture. So machine learning helps us to do yield prediction, which we did. It helps us to detect disease and pest detection, which we can do. This would become a classification problem. It helps us to optimize resource allocation for crop management as well, soil analysis. You can do prediction on different nutrient levels. We have this data set as well, so we can do prediction. Now, when you are doing prediction, again, remember that you are doing machine learning and you are selecting the algorithms that help you. So what type of machine learning is there? Sometimes we use these methods without knowing what they are. So we have basically 3. We have what we call the supervised learning and unsupervised learning, which are very common, but we also have the reinforcement learning. So what's the difference between the 3? Let's start with supervised learning. So it trains the model using labeled data where you know the outcome already. Okay, so the model works by comparing what it predicts and what we see. For example, what we did today, we had already the yield categorized as high and low, and we did our predictions, and we are basing on what was there to know if what we are doing is right or wrong. That is supervised learning. So we know what the outcome is. So we do a prediction and we can compare with what the outcome should be. Now, unsupervised learning on the other side is where we do not know what the categories are or what the outcome should be. So the model will just try to find similarities and group them together and create patterns that look the same, basing on the data that we have. For example, clustering, okay? So you could use clustering, for example, in marketing, basing and then classify your customers basing on their, for example, behavior, okay? So you pull out information that makes them similar and put them in different groups. Then you can name the groups after. So you do not have prior groups, but the algorithm that you choose helps you to identify, and then you look at characteristics and you are able to say that these ones look similar, they behave like this, we can name them this, okay? That's the difference really between supervised learning and unsupervised learning. So when you're doing things like linear regression, like we did yesterday, all that is supervised learning because we know the outcome. We have an outcome. So we are judging the model on its performance basing on what we know that the outcome should have been like. Now we also have reinforcement learning. Now this one here, the model makes decisions by interacting with the environment. So it does a lot of trial and error until it finds which one is correct. So reinforcement learning is mainly used in things like robotics, gaming, various autonomous systems. In this training, we may not concentrate on reinforcement learning, but we are surely going to be concentrating on supervised and unsupervised learning, which we have already started. So as I said earlier, supervised learning means you know what the outcome should be, okay? So you check if the model can identify what the outcome should be. In other words, the data that you supply is labeled. For example, here, if these are animals, you know that this one is an elephant, this one is a camel, this one is a cow, okay? Now, the algorithm that you choose and train should be able to say that this is an elephant, this is a camel, and this is a cow, okay, correctly. And then you would know whether the model is working or not. If the model fails to identify this as an elephant, then you say the model is not good or is not accurate. If it fails to identify this as a cow, that model is not accurate. In our case, we already knew the classes as well. So we want to know if the model can correctly identify existing classes. Unsupervised learning, on the other side, is there are no labels. We don't know what this is. We don't know what this is. We don't know what this is. We want to know if the algorithm can differentiate them. Yes, they are different. It doesn't know what they are, but the aim is to know if the algorithm can say that this image is really different from this one, it is different from this one. If you had a group of people, it would say group 1 is really different from group 2, is really different from group 3. Because the data is not labeled, we don't know what group 1 is. We don't know what the output is, but we know that they are distinct from each other. And those methods are there. Those are the methods like clustering, which we are going to see. So we also talk about algorithms in machine learning. And we want to know, what do you mean when you say an algorithm? An algorithm is just a method. It's a method that the model uses to learn from the existing data. So these methods that we've been talking about, the models, we also refer to them as algorithms, and sometimes we classify them according to what they do. For example, classification, if the model classifies information in two groups, then that one is called a classification algorithm. For example, the logistic regression model, we used it to classify predict groups, high, low. So the logistic regression is then referred to as a classification algorithm. Okay, we have others like the support vector machines, the decision trees, neural networks. There are so many, you will come across them. Sometimes what you need is the simplest algorithm, like the logistic regression to classify. We have others that are used to predict continuous outcomes, which is regression. But we have examples like the linear regression, but it's not the only type of regression that exists. There are so many types of regressions that exist out there. We have the ridge regression, we have the lasso regression. But if you're predicting a numerical outcome, then what you're using is called a regression algorithm. Just because we chose to use linear regression does not mean that linear regression is the best algorithm for predicting continuous outcome. You can use a linear regression, use a ridge regression, use a lasso regression, and choose among those which one performs best. Even in classification, you can choose to use the logistic regression, use a support vector machine, and check which of the two does a better classification and choose that model. Okay. Likewise, in regression, you can choose a linear regression, you can choose another one and see which one performs better, and you choose that one to do your prediction. Okay. So it is not cast in stone that you should use linear for numerical or logistic for categorical. It's just an example of one of the algorithms that you can use to do classification. Okay. We also have clustering algorithms. These ones help us to put coins together, as I said earlier. Okay, you can group information that you do not know the groups they're in, but they are clustered according to certain characteristics that exist in the data. So what you need mostly is to have data, then you can be able to extract different clusters that look similar, and then you can be able to understand or pick out some important insights from your data set. So there are many types of algorithms that help us to do clustering as well. We have the k-means, we have the hierarchical clustering, and you can choose any of them to do your clustering. And when you choose them, you then evaluate if the model is performing well and choose the best model. Okay? But you cannot choose a model that is doing something else that is not clustering. For example, you cannot choose to use for an algorithm like logistic regression here, because that is not what logistic regression is designed for. So when you're choosing algorithms, make sure you are choosing an algorithm that is designed to perform what function that it's designed to perform. If it is clustering, choose a clustering algorithm. If it is regression predicting out a numerical outcome, choose the right algorithm for the machine to learn, and then you can evaluate them. We also have algorithms for dimensionality reduction. Now, when you're dealing with data science, you tend to have big data, large data sets. So sometimes it's very difficult to go inside the data set, try to extract information. You can have 1,000 columns of data, and you need to be able to pick out something important from that data. You are not going to run a model that has 1,000 predictor variables, for example. So when we are dealing with large data sets, we need methods that help us to extract as much information from that data as possible, condense it into smaller data sets, possibly put them into 1 or 2 variables, and use those variables to do prediction. Okay, so there are a number of methods that help us to do this, and we have a popular method called the principal component analysis. the principal component analysis is a dimensionality reduction. It helps us to condense information when we have a lot of information so that we can be able to quickly visualize and to quickly extract information from large data sets. Okay? So with that, I would like to hand over to Stephen so he can take us through the next session, and then we continue with the series. Thank you, Stephen.
Thank you, Peace. Thank you, everyone. So we have been covering predictive analytics, and the next 2 days we'll conclude with prescriptive analytics, because when we introduce data science, we mentioned that we have 4 types of analytics plus generative AI. So the last 2 days, Peace has been discussing predictive analytics. So before I go to prescriptive analytics that we'll see in a few minutes, I would like to take you through how do you evaluate the performance of these methods. We'll go through that, and then also I will discuss one last method of predictive analytics, that's the post-vector machine. And then we'll go and spend the rest of the afternoon talking about QGIS. But before we do that, let me share my screen. We would like you to install, download some few data sets. So please download a data set called country underscore CO CSV, and also download other script called SVM underscore linear. You downloaded other script called performance evaluation yesterday, but if you haven't downloaded that one, please download that. And then there's a file called Kenya Agri Prediction underscore A GPKG. So be using that file when we are working with QGIS. Okay. So the first file that you have to download is called country underscore co.csv. And the second one is SVM underscore linear. That's a new file. But there's a file that you have downloaded yesterday is performance underscore regression.r. And the last one is Kenya Agri disease special underscore A underscore GPG. So you can download those files, then we can continue, okay? So you put in the chat if you have downloaded them. I'll be watching. I'm going to give you another 1 minute. Okay, so the last 2 days we talked about regression and classification. So those are the 2 methods in machine learning. But how do you know that your method is doing a good job? So there are ways of how to evaluate those methods. So if we're going to start with we're going to start with regression. So how will you explore how to measure your model? So if you're predicting numbers, you're working regression. If you're predicting categories, you're working with classification. For example, when we're predicting milk yield, that was a regression problem. And then whether a cow produces either high or low yielding, that was a classification problem, okay? Okay, so we're going to work with a data set called animal_data.csv. We've been working with that set a long since I think Tuesday. So if you open your R script, you can download that data for now, but we'll run that data later. So think about that data set that is you're opening a spreadsheet that has all information about animals and the results. So that's the data set we're going to use. And I think
Stephen,
yes.
we are not seeing the presentation.
Okay, so let me go back and share my screen here. Are you seeing it now? Are you seeing the presentation now?
Yes.
Okay. So let me start again. So last 2 days, we were talking about predictive analytics. And predictive analytics has a regression or classification problems. So how do you evaluate those two? So evaluate them by what's called performance evaluation, okay? So when you're talking about regression, what it does, it predicts numbers. This is an example. When you're predicting milk yield, that was a regression problem. But when you're predicting categories, and we saw the two categories were high yielding or low yielding, it's a classification problem. So in machine learning, when you're doing predictive analytics, you're dealing with these two, many regressions, predicting numbers, and classifications, you're predicting categories. So for this, especially the regression part, we're going to use this data set called animal_data.csv. I think you guys already have the data in your data_science folder. So think about that data that you're opening a spreadsheet that has information about animals, okay, with different details. So whatever you're going to do, you're going to do predictive analytics and find out if your models or your methods is working to help you dealing with those animals, okay? So, but how do you work with those data sets that I've told you to open? So when you're working with data set in data science, you have different methods of training. So the first one, you train your data, you train your model using the same data, and you test. For example, I have these data sets here. I put them maybe in a cycle here. So what we have 12 items here. So number 1 to 12, and you have variable x1, x2, and x3, and you're supposed to predict your y variables here. So what you do, you use all these items in the cycle here. You train your model. After training your model, the model will learn from all the 12. And then from that, you predict. You predict each of them. So the y is our original. So after training, the model predicted 20 to be 18, 11 to be 9, 12 to be 13, and so forth. So with this, you train your model using everything. So you train using the training data sets is what you use for testing, okay? Another method that we use for training is called leave one out or cross-validation. So I'm going to start with leave one out. Then in the next few slides, I'll show you what you do. So in the previous slide, I told you that you train your algorithm in all those 12 items, and then you test them. But with leave one out cross-validation, you pick one out, you train your algorithm on the 11, you test on that one that you left out, you get the information, you put it out. And then you put, after getting that information, the output, you write it down. You put that one back, you take the second one and train like until you're done. So that's called leave one out cross-validation. And then there's also leave k groups. So what you can do, if k is 3, you take 3 out, you train your algorithm with 9, you predict the 3, you put their values, you put them back, and you pick another 3 until you're done. So most of the time, what's done is they always do in multiplication 5. Sometimes they call leave 5 out cross-validation, leave 10 out cross. It depends also on your data sets. So this method is mainly used when you don't want to train all your data and then test your algorithm in all the data sets, okay? And then after doing all the training, you average the results to give you that accuracy. What we're going to talk about accuracy in the next few minutes from here. Okay, so this is what I've just been explaining. This is leave one out. So we took 12 out, and this 12, number 12, our original Y was 33. So we use this 11 and train. So so we got number 12 out. We did our training using X1, X2, X3. And then after building the model, we use X1 that was 8, X2 8, and X3, and then our predictor became what, 31. And then we put 12, you put 12 back, and then you just pick a number, maybe you pick 6, and then your training now, your training will include number 1, 2, 3, 4, 5, up to 12, excluding 6. Okay? Okay. So this is K cross-validation example K form. So what you do, you leave this 1, 2, 3, 4 out. Okay? You train your model using this 8. And then this model, use this information, and then you predict these numbers here. Okay. So those were what I just discussed were leave one out, okay, cross-validation. But most of the time, especially in data science, there's what they call train and test split. So what you do, if you have enough data in your sample, you split your data into 2. Into training, and that training will learn. The model will learn from that training. And testing will check. So testing will not include any, the algorithm will not know anything about the test. And always it's 70 to 30%, but some people go 60-40, and some people go 50-50. So the test results that you use, it's not seen by algorithm, okay? So this is an example here. So we pick this and train, remember cross-validation, you put them back. You pick this train. After training, you don't put any of them back. After that, you did the prediction, and that would be your prediction. Okay. So now, any of those three methods, as I just discussed, how will you know if your method is working? How will you know? Because what you're going to do is you're going to train the algorithm, and then after that, you're going to do the prediction. So there are few methods here that people use. One is called root mean square error, and then it's called MAE, and then error square. So how do you interpret those? So for RMSE, it interprets how far predictions are from the real value on average. So remember when we did the first leave one out, our original Y was 30, and we predicted 31, okay? So you get the difference between your original and the predicted one. So it measures how far predictions are from the real value on average, okay? And then MAE, it's made the average error without worrying about positive or negative. And R square is how much of the variation in the results our model explains. So the smaller RMSE and ME is the better. So if you build your model and you use it to test, and you get a smaller RMSE or MAE, that's the better. But with R square, the closer to 1 is the better. So basically, when you did your prediction, you look at the results, the smaller RMSE is the better. And then the closer R to 1 is better. Okay? So we're going to go in RStudio now. I requested you to download this performance underscore regression. So we're going to run that, and then we're going to look at our results, okay? Let me go to RStudio now. You open your RStudio. So this is our animal data. This over here. So you let me know, you type in the chat if you have opened this script here. Okay. So the first thing we're going to do, Chris already shown you how to run this script. So I'm just going to go fast here. So basically we are reading this data called animal underscore data. And if we're going to give information from the headings, okay? And then after that, we are going to, the categorical variables, we are going to make them as factors. And then we are going to all these are just cleaning up the data, okay? And then we're going to fit regression. You guys already did this. And our dependent variable is milk yield. And then after that, we're going to run. And we're going to predict our predictions. Our prediction is going to be y hat. Our true value is going to be y hat true. Our prediction is going to be y underscore hat. And then after that, we're going to do this matrix of RMSE, MAE, and R squared. Okay? And then this cat merely telling them to produce them so that we can read them. Okay? So I want to run this just fast. What happened? You guys see my screen? Something happened. Hello, do you see my screen?
Yes.
Oops, the screen seems like disappeared here.
Maybe you stop sharing and you share again.
Okay.
Stephen, you haven't yet stopped sharing, so you could just stop sharing and then reshare the actual screen.
You see the screen now?
Yes.
Is it better? Okay.
Yes.
So these are our results. So these are intercepts, and this Chris already explained this when she ran a regression. And this is our R square and R adjusted. You can see it's high. Okay. Our R square is high. And then you see our prediction now. Okay. So I'm going to explain this plot too. So this is our root mean square of error is 5.49. Again, our R square is here, which is 0.98, which is close to 1. And this is MAE, that's also smaller. Another thing that I want to discuss is the graph. So this is residual graph. So when you run your regression, your residual graph and the physical graph should just be like random. But this is our fitted. You can see our predicted yield is on the y-axis, and our actual yield is on the x-axis. So if you draw this straight line, that means our model is doing a good job. At least you can see this line here. So there are four ways of evaluating your regression: root mean square error, MAE, and R square. So this one should be smaller, so it should be bigger, and then also when you plot your residual and fitted, it should be scattered like this. Okay. So this is about how you evaluate your regression. So when you have different methods, this is what you do. You call the performance of each method, and then you see the RMSE, MAE, R square, and also the residual plot. Okay. So that's how you evaluate your regression. So let's go back to our slide here. So that was about regression. So next, we're going to go to classification. Okay? So classification. So classification piece talks about what's logistic regression. So those are for categories, okay? Okay. So you predict categories. In our example, we had low or high yielding. We use a logistic regression to estimate probability of high yield. Of course, we pick the threshold to decide we did that, okay? Okay. I'm going to represent this just by train and splitting the data sets. So we train our data sets and test data sets on 30%, okay? So it's the same as regression. When you're doing training and testing, you're not going to put testing back. But now we're going to introduce new terms here. You have to show accuracy and other matrices for the test data.
Stephen, we are not
Yes.
seeing the PowerPoint. If you're showing a PowerPoint, we are not seeing it.
You're seeing now?
Yes.
Okay. So as I was saying, in the classification, as we did in regression, we're going to split the data into two. We're going to do our training and test, and we're going to split 70% for training and 30% for test, okay? And we're going to use another term here which is called accuracy. And this is one of the metrics that we use for testing how the algorithm that you train, use the training data sets, is going to test on the test data set that has not been seen by the algorithm, the training data sets. So why do you do that? Mainly when you use training, you train using training data set and test using test data set, you're preventing what's called overfitting. And overfitting in a layman's language is basically making machine learning just memorize what is training instead of learning from it. So sometimes when you do train, you get very, very good accuracy when you test on your training data set. But now when you get new data sets to test the algorithm, you get very, very poor results. So that's what's called overfitting, because basically the machine learning is memorizing the variables for the training, okay? Okay. So calibration plot. So this check if predictability, probability match reality. So for example, if you say 70% chance of high, does it really happen 7 out of 10 times? Okay. So good calibration means predictions are trustworthy. So that's why sometimes when you are working with people and you present your results, they'll ask you to explain the calibration. So basically what they're trying to say is that's your prediction, what we've done, is it trustworthy? Okay, so this is another word that I'm going to introduce here, a confusion matrix. So what's a confusion matrix? So when we did regression, we didn't talk about a confusion matrix. When you're doing regression, you're predicting continuous variables or numbers, but now you're predicting categories. So a confusion matrix is basically a 2x2 table that compare your model prediction versus actual labels. So I'll take you back again to what I presented in those circles, those 12, and then when we trained our algorithm, we left them out, we tested on them, and then you compare what was in Y and what was predicted. So terminology that is used in confusion metrics. So true positive, that's always presented by TP, is when we are predicting mesoil to be high. So on RY, let me go back here. On this Y here, if this is like high and low, when your Y is, the reference is high, and then your algorithm predict that to be high, that is true positive. So when Peace was teaching logistic regression and she presented her results, you could see that some were presented high, but they predicted were high. So those were true positive. And then as you went down, you could see that some, the original were high, but the logistic regression predicted them as low. Those were false positive. And then the false negative, so when she was presenting her results, so some places the actual yield was low, but it was predicted as high. So that's your false negative. And then true negative is when the actual, the historical data that Peace used for predicting was low, and the actual was low. So these four terms always confuse people. So the true positive is when you collected your data, and then after those data, you have your, you know that this column, it has high, number one is high, number two is high, number three is low. And then when you train your algorithm, like when Peace presented, she trains logistic regression. When it is high and the predicted is high, that's your true positive. When it's high and it's predicted low, that's your false positive. And then it is low, and then predicted that's high, that's your false negative. And when it is low and it's predicted as low, that's your true negative. So these four are very, very, very important matrices that people use them in medicine, in agriculture, you name it. That's where the sensitivity, specificity come from, these four, okay? Okay, so in table form is put like this: predicted high, actual high, true positive; actual high, predicted low, false negative; actual high, predicted low, false positive; and actual low, predicted low, true negative. Okay, now from those four, you can now talk about accuracy. So if people are talking about accuracy in machine in data science, accuracy is the number of your true positive plus number of your true negative divided by your total. Because if you had true positive plus false positive plus false negative plus true negative, this is your total. So your accuracy of your algorithm is your true positive and true negative divided by your total sample. So what's true positive? The true positive is the real, like if you go back here, your true positive is high, the actual is high, and the predicted is high. And then your true negative is the actual is low and the predicted is low. So if you add what you counted here plus this one here, you add them together and divide by the total, that gives you your accuracy. So always you want accuracy to be a little higher because it's capturing your true positive and your true negative. Okay? So, but this is the caveat though. If you have imbalanced data, then you're going to have error because sometimes if you have fewer of the others, you're going to introduce errors in what? In your accuracies. You have to make sure that at least your data set is a little bit balanced, okay? Okay, positive predictive value. So what's positive predictive value? This is all predicted high, and then how many are true high? So this becomes like this, which is sometimes called precision. Is here true positive plus true positive plus false positive. So if you go back to this table, it is here true positive divided by the true positive and false positive, okay? And then recall, which is sometimes called sensitivity, which is true positive rate. If all the actual high, how many did we correctly predict? So the formula is here true positive divided by true positive plus your false negative. Okay? So when you miss many positives, it's going to cause you to detect what? Truly high yielding animals. So that's why it's called sensitivity or recall. How sensitive your method? You divide your true positive, divide by true positive plus true false negative. And specificity is just true negative rate. So especially in medicine, sometimes they go between sensitivity and specificity. So for all actual law, how many did we correctly predict? That's your specificity. Is your true negative divided by your true negative plus your false positive. So there's a relationship with false positive rate is equal to 1 minus what? Specificity. Okay? Okay. Sometimes you visualize this in heat map. So I wanted to bring this here. So they always make it the darker the colors, that means the more the cases. It's easier to explain than in a table. Okay, so for example, this is an example here. So you have your confusion matrix, and your true positives were 40, false positives were 10, false negatives were 20, and true negative were 30. So your total, sum this up, is 100. So when you use R, you don't have to do this calculation. But when you run your R or any other software and you find this, it gives you all this information. This is how the calculation is done in the background, really. So your accuracy is your true positive, which is 40, plus your true negative is 30, divided by the total, which is 100. So your accuracy is 0.7. And your precision is your true positive plus true positive divided by true positive plus false positive, which is 40 plus 50, plus 40 divided by 10, which is 50. And your recall sensitivity will be your 40 divided by 20 plus 40, which is 0.67. Your specificity is your 30 divided by 30 plus 10, which is 0.75. So in other words, your sensitivity is basically deal with your positive, true positive, and your specificity when you deal with true negative. Okay? So I wanted to bring this in calculation so that when we run our script, we'll see where they come from. So the calibration plot for test sets. So this is basically it's like confusion metric, but it's always using test data sets. So basically, it's a visual version of confusion matrix. The darker colors, the more cases, and easier to explain, like when I explain in the heat map. Okay, so the next thing that I'm going to introduce here is receiver operating characteristic curve, which is ROC. So this again comes from those four matrices that we discussed. So on your X, you have your false positive rate, which is your sensitivity. On your Y, you have your recall, which is just your specificity. So when you plot them, this is what you get. So you start from 0. As you increase your true positive rate, this one's also become higher. And then, so a perfect one would be just like this, 1. But if your curve is around middle here, that means your method is basically, it's not doing a good job. So a good method, the curve has to be probably more than 0.5, and then the area under curve should be greater. So if you talk about ROC curve, again, it comes from those 4 matrices that we talked about. So on Y, your true positive rate, on X, your false positive rate. Okay? So how do you build it? So you vary the classification threshold. Okay? So it's mainly done by computer, but you vary your scores or probability. And then you have this area under curve. So if it is random, you get 0.5. It is 1.0 is perfect. So the higher, the better. So curve closer to the left are better. That means the algorithm or the method is better. But curve that close to the diagonal is basically random. So that's how we also compare classifiers. Because this one, what we are discussing now is basically for classification. You cannot do this in regression. Okay? So ROC curve is mainly used, especially in medicine, because when you're dealing with medicine, you have to give and take. So are you going to go with sensitivity or are you going to go to specificity? So that's always, you have to, there's no straight cutoff. It depends on the field, really. So that's why one field, some people may say, okay, 0.7 is good enough. Some people may say 0.8 is good enough and so forth, but not 0.5. Okay, precision or recall, you just focus on high predictions. So the precision out of all predicted high, how many are correct? Already see that. We've already seen that. So out of all real high, how many did we find? Okay. Another important metric that we use is called threshold sweep. So this shows how accuracy, precision, recall, specificity, and F1 change as threshold moves from 0 to 1. So sometimes, especially in car manufacturing, when they're using, when they bring parts, they use this to accept certain part of cars, because cars, when they're building them, they always work in millimeters for a part. So sometimes they use this threshold sweep. So you start from 0 point something, you go to 1. So it helps pick the best threshold for the situation. Okay, so with that, I'm going to stop here and go to support vector machine. And then in support vector machine, that's when I will talk more about what we just discussed in classification. Okay? So let me get my slide for support vector machine. Please, do you still see my slide? Anybody seeing my slide? Type 1. Okay, thank you. So I just finished talking about performance evaluation. We talk about how you do for regression, and then we talk about how you do for classification. But before I move to prescriptive analytics, I wanted to introduce support vector machine. This is one of the best methods that's used in machine learning. There are the three types of support vector machine. There's linear, radial, and polynomial. But because of time, we're going to talk only about linear. Okay. So what's support vector machine? So I'm going to show this by talking about two fruits. I'm going to talk about apples and oranges. Okay. So imagine you have apples and oranges mixed together on a table. So apple here, I'm going to present by red, and oranges by orange color. So what you want to do is draw a straight line on the table so that apples are separated on one side and oranges on the other side. So what support vector machine does, it draws a straight line to separate the two fruits, basically, what it does, okay? So, but it draws several lines. It's not just any line. So what support vector machine is looking for is the best line. So there can be very, very many lines that are drawn between apples and oranges in that table. But it's looking for the best line. So out of those lines, what a support vector machine does is it picks a line that will leave at the biggest space between the apples and the oranges. And that space is called margin. Okay? So the bigger the space, the more confident is support vector machine. So it just keeps drawing lines. Okay? So these lines are called margin. Okay? So this is just an illustration. So here, you have our apple on the left, you have oranges on the right. So we start drawing, you look at the red line. So it's drawing here, but this red line is closer to apples compared to oranges. And then another line is the blue line, means the black line, the black line. This black line is closer to oranges compared to apple. But if you look at the blue line here, this blue line is not very close to apples and it's not very close to oranges. So this is the line that gives the biggest space, the biggest margin between the apples and the oranges. Okay? So that's what support vector machine is doing. But if you go to the other ones that we're not going to talk about here, instead of using straight line, they use kind of like a curve to go through that. Okay? So it selects the best line to separate for the classification. So how does it work? So SVM imagines a boundary that far from both groups. So the closest point from each group are called support vector machines. So they are like referees making the edge of the field. So we have this line separating the two fruits, okay? But each fruit also, each fruit, the apple, they also have a line that is very close to them. The middle one is the one separating them. But there's also a line that's close to this apple. There's a line that's close to these oranges. So those lines, so if you have an apple that touches that line, that becomes the support vector for that, okay? So they're kind of like referring, okay? So this is the decision line for Apple. So this is the this is the middle line that makes the widest margin. So this is the line for apple and this is the line for orange. So any point that touches here, these are any of the fruit that touches here, those are the support vector machine. That's why if people are trying to define support vector machine, it said reduce dimension from high to low. So you don't use everything. The few that are touching the support vector machine are the ones that are going to the ones that are going to be used for algorithm, from high to low dimension. Okay. So this is what the support vector machine does. Measure two things about each fruit. For example, it's going to measure the weight and color of shade of the fruit, and then plot them on a chart. Apple class in one area, orange is class in another area. So the job of support vector machine to find the best straight line or curves when we're talking about polynomial or radial, that divides apple from oranges. Maximize the gap between this line and nearest fruit from each side. This gap is called the margin. Support vectors are the fruits that sit right to the edge of the margin. They support the line's position. When a new fruit comes in now, the support vector will check which side of the line it falls on to decide if it is an apple or an orange. That's the classification. So how will they decide? Because here we are using two categories here. We're using the weight of the fruit and the color. So the color of the apple here is red. The color of the oranges is orange. So you take the color and you take the weight, okay? And then you plot this, and then you find the margin, and then you use those that are on the edge, okay? So when now you develop the algorithm, if you bring a fruit, if it is orange, the algorithm using this information will tell you this is an orange. If it is an apple, the algorithm will tell you this is an apple, okay? Okay, so let's go now to the equation here. So this is the rule. So the linear SVM will classify a fruit based on this equation here. So this is our prediction for the predicted Y. The sign of weight times X is like our weight, our color, plus B. So WX is the dot product of the weight vector with the fruit and future X is what, so what we do is we calculate B, which is the bias term that shifts the boundary, okay? So this equation here is the one that will determine which side a fruit will be, okay? So this is another example here. So when you are now training your model, you're going to give one group a minus and one group a plus. That's how you're going to label them. So for apple, the label will be a -1. For the orange, the label will be +1. So the blue solid line, this one here, is our decision boundary, and it's represented by this equation here. Your dot product plus B is 0, this one here. And the blue shaded line are the margins. So now if you multiply your dot product times B, if it is negative, if it is a negative, it will be what? Your apple. If it is positive, it will be your oranges. Okay? So the equation that that I presented in the previous slide now comes in here. So the blue line is your decision boundary, which is your dot product plus your B will give you 0 here. And then the dash at the boundary where the support machine will be being calculated on. So if you multiply after getting these are your variable, your x variables, like the weight and the color. Then if you add to this and you get a negative, that fruit will be an apple. If you get a positive, that fruit will be what? An orange. Okay? So the separating line basically already explained that. The boundary between apples and orange is this. It should be 0. So if after calculating, you get a plus, will be an orange. You get a minus, will be an apple. So in essence, that is basically what support vector machine is doing, is using information from the historical data to model the future, and it uses this equation here. So how do you use this in agriculture? On farm, support vector machine can be used to identify disease and healthy plants by using only leaf measurement. You take the measurement from the leaf. For example, when you're using things, drones or rovers, you can just do that, you train those algorithm, and then it will separate them. Also separates fertile versus light petals for planting, classify soil sample into where they need fertilizers or they don't need. Also smart harvest for export versus the local market. And other areas that we use support vector machine. Okay. So this is basically, in a nutshell, in a layman's language, is what support vector machine does. Okay. So now we're going to run a script for support vector machine. And this script is, if you're seeing my RStudio type 1, okay. So we're not, because of time, we are not going to go through that, but I'm going to run, you can run this in your free time. So this script, I wrote the script, I think has like, how many lines? 70 something lines. So I'm going to run this script, and I'll just show you the W, the B's, and the A's. But in the beginning, I will just show you where the data is coming from. In your free time, you can run this script, okay? Because we need to go to QGIS, okay? So I'll go briefly. You have to install the package for support vector machine, this line here. When you're using the script, because I have a hash here, because I already installed support vector machine. But for you, you haven't installed it, remove the hash and install support vector machine, install a package for ROC, and also we already installed this. So I also introduced this. You can install several packages at once, okay? You can install several packages. What you need to do is just do install.packages, open bracket, and put C. This C is in R is called concatenation. Put C, open bracket, put the name of your package in double bracket, in double quotes, comma. The second package, again in double quotes, comma, and so forth. You can install as many as you want. So before you run this, if you don't, because the script you downloaded, I have hash here, because I want to run this so that it doesn't install for me again. So in your free time when you're running this, make sure you have this installed. So I'm going to call my support vector machine library. I'm going to call my ROC library, and then the data set I'm going to use is animal_data.csv, okay? The rest is just cleaning up, okay? So because of time, I'm going just to run this, and then what I wanted to show you is I want to show you the W, the C, and also discuss with you guys the true positive, true negative, and ROC curve. Okay, I'm done. Okay, so as I said, in your free time, you can run this. You have the data, you have the script. So you see these W's that I showed you when I was talking about oranges and apple. So every variable with its own W's. This W is for feed intake. This W is for age and month, and every variable with its own W. And then we have only one B's, okay? This one B is here. And then now we're going to use all the variables. So let me see if I can get this data here. Kenya animal. Let me see if I can view it. Switch data here. Because I'm going to take you back to that equation that I showed you. This animal data. I want to view it here. View data. Okay. So this is our data. So these are the variables. So in our example, when I was discussing, these are like the weight of the apple and the color of the apple. So these are feed intake, age in month, and so forth. And if you look at this, this is the W for feed, this is the W for age, this is W for body weight, okay? And so forth. So what we're predicting is this one here, okay? So we have the W's are here for each, and you have the X's are these guys here, up here. These are all X's. And then there's one B here. This is the B. So if I go back to my slides, if you see my slide, you type 1. Type 1, my slide. Okay. So if you go back to my slide, okay, let me go to, if you go back to my slide, you see this? So the X's are the variables that we have, and each variable has its own W, and we have only B1. So anything that was greater than 0, it was high. Anything that was less than 0 was low. So that's how ARA did the work there. So I want to share that with you. Okay, so I'm going to go back to my ARA Studio now. Okay, type 1 when you can see my ARA Studio. Okay, so let's go back and look at our confusion matrix up here. Okay, so this is our test data sets. You can see the actual, this is our actual low, predicted low, this is your true negative. Our actual high, predicted high, this is our true positive. See that? And this accuracy came from that. And this is your area under curve, this one here. And this is the difference. Remember when I was discussing performance evaluation? When you use your training data set, sometimes you're going to have overfitting. You can tell from here. Let's look at this graph here. So these are our ROC curve. This is our specificity, this is our sensitivity. So this is basically about positive, it's about negative. So the algorithm, the support vector machine was trained on training data set and tested on a test data set. You can see here, our area under curve is higher. But now, this is basically misleading because it's being overfitted. But this one now is tested on test data set. This was not included in the training, you can see it's lower. You see that? It's 0.728. So it's always good. It's always good to, if you're testing methods, to do both. Do the training and do the testing, because the training data sets, it was trained on the training and tested on the same. But this test data set was not included in the training, okay? So that's the ROC curve. So how did you come up with this ROC curve? We came up with that from this. This is test performance here. Our true negative, true positive, false positive, and false negative. And then Ara did it in the background, okay? Okay, so I've shown you how you can calculate linear support vector machine by hand. I've shown you when you run, you're going to run this in your free time, give you all the W's for each variable. And that's your dot product. Your dot product will be the weight of feed intake in kilogram times, if you go back here, times this variable of feed for this, okay? And you go in all the from the first row to the last row. That's what Ara was doing in the background. So this is the weight of age in month. It has to be multiplied with all these variables, and then plus B. B is here. And then it'll tell you, okay, put this on this, put this on that, put this on this side, put it on that side. Okay? So with that, this is the end of our predictive analytics. So now we're going to go to prescriptive analytics. So after doing all this, we have to make people use what we have done. So the next few minutes that's left, and tomorrow, we're going to do prescriptive analytics. We're going to start with QGIS. And then after that, tomorrow we're going to do Shiny, okay? So I'm going now to get out of ARPA now. I'm going to go to my QGIS notes here. So there's a file that I wanted you to download. There are two files. One was country_co.csv, and there was another one, predicted analytic output for QGIS. If you can get those two files for me, will be okay. Okay, if you can see my QGIS slides, type 1. So from now on, we are going to do prescriptive analytics. We are going to deploy our model. Good. So I suppose you have your QGIS already. Please open it. I'm going to give you at least a minute. Open your QGIS before we start. Okay. What's QGIS? QGIS stands for Quantum Geographical Information System. And this is a free software. It's open source desktop for geographical information system application used for viewing, editing, and visualizing geospatial data. That's why we are using, the data we are using has coordinates. It has longitude and latitude. So it supports different file formats, support vectors, file format, raster, it supports comma separated values and others. So we're going to use two file formats. One is a vector and one is a comma separated value. So it's a very powerful tool. but it also has a very deep learning curve. But it's a very, very good tool. So it offers spatial analysis, geoprocessing tools, and map creation. It also integrates plugins for advanced workflows, uses global positional system, GPS, okay? So I would like you to open your QGIS, and these are a few things that I would like you to learn this afternoon. So if you open your QGIS, I will also go back and open mine, but before I want to just to let me know if you can see what's called plugins. Okay. And then there's a layer. And then there's coordinate reference system. And then there's a place where we're going to be, our map will appear. Okay. So let me go and open my QGIS. And I would like you also to open your QGIS. If you see my QGIS, put one. Okay. So if you open, I would like you to make me know if you can see the plugin, where my cursor is. And the space here, that's going to be our layer. If you don't see the layer, I'll tell you what to do. You should see something like layer here. If not, I'll tell you what to do. We'll get layers here. Okay. So after this plugin here, right now we need to have the plugin and we need to have layers. So if you can see the layers, go to View, go to Panels, and click on Layer. If you can see your layers. You see where my layer is, I have a tick. That means I can see it, because those are very important before we do anything else. I need you to be able to see your plugins, and then on here, on your left, I need you to see layers. Before I go back to my slides. Open your QGIS. I would like you to, you have layers here, and then so you have to have a plugin. Okay? Give you a minute.
Stephen, somebody's not
Yeah.
seeing their layers.
They're not seeing the layers. Okay, so you see my cursor? I mean, you see my cursor? Go to View, go to Panels, and click on Layer. View, Panels, Layers. View, if you click on View, you're going to come back down here, you're going to see Panels. You see if you see your panels, you're going to see layers. Okay? Are you with me? Okay. So I just wanted us all to have our QGIS app. I'm going to go back now to my slides. If you see my slides, type 1. Okay. So when you work in QGIS, you're going to work in what's called projects. So a project is basically a workspace. So this is where you organize and store all the elements that you're mapping and analyzing. So it includes where your layer configuration. And the layer, you can have vector, raster layer, and so forth, which we are going to see. It has coordinate reference that define the spatial reference and projection settings. There's a map layout. That's where you can save your map for printing. There's attributes for data, and it also has plugins and other tools. But for us, we are mainly interested in the plugins and layers, okay, for now. So every work you do in QGIS is like in a project like what we're doing in R, okay? So plugins. So what are the plugins, by the way? So the plugins are like your R packages or R libraries. So it adds extra tools, like when you're using R or R Studio, when you download R Studio, actually come with certain packages pre-installed. It's the same with QGIS, but sometimes you have to install, I call the plugins, okay? So example of the plugins is quick map servicing. So this one is used to just to generate what? Base map. We're going to do that. We're going to install that because this one doesn't come with QGIS unless you already installed it. So the plugins, just think of plugins as your packages in R. Okay. So how do you add plugins in QGIS? We're going to do that together. You already open your QGIS. Okay. You're going to go to the plugins menu. You're going to click on the plugins on top menu. We're going to select manage and install plugins. And we're going to search for the plugin that we would like to install. Okay, we're going to do that together. And then when you search for the name, for us, we're going to install this plugin called what? Quick Map Services, okay, because we're going to use that. So what we will type that Quick Map Services, okay? And then when it comes, we just install it. It's as simple as that. Okay, so let's go to our QGIS. Okay, so type 1 you can see my QGIS. Thank you. Okay, so we're going to install plugins. Okay, so see my cursor? Click on plugins. Manage and install plugins. Okay, let's go back. Click on plugin, manage and install plugins. And then you're going to type here, quick quick. See, quick map services. Okay, quick map services. Quick QIC. See this one here? Mine's already been installed, but it will come. If you click on it, and then because mine's already been installed, so I cannot, unless I install it. But if you click on that Quick Map Services, it will bring for you install, and then you click on that and it will install for you. Okay? Let's go back. Plugins, manage install, and just type here. You start typing Quick Map, the Quick Map Services will come, and you click on it, and then you install. Okay, those who have installed, you type 1. Okay, I'm going to go back again. Plugin, manage and install plugin. You know what? Let me uninstall mine first. I think that will help. Okay, I'm going to install mine. Okay. I'm going to install my plugin. Okay, it's gone. Okay, let's do it together now. I don't have it. Go to plugin. You see where my cursor is? Click manage plugins. And if you type this, mine's already here. If I click on this, you can see here. You see my cursor? You click on install plugin. We'll just take a few seconds. It's done. So now the install is gone. Okay. Have we installed it? Okay. Okay, so this is it, what I just explained. You click on manage and install plugin. You type it here. You click here and install. Again, plugins, manage plugins. Type this one here and install. I'm going to give you 2 minutes. Okay. So how do you use this QuickMaps plugin? So to use your plugin, now you go to the web, you click on QuickMap Services, you go to OSM, and you click on OSM standard, and that will be basically your library. So what will it do? It load your base map in your QGIS project. Okay. So to use this plugin is like in ARA, you have to write, like you install your package, then you write library, you give it the name of the package. This is similar to that, but to use your plugin, you go to your QGIS in the web, you click on Quick Map Services, click on OSM, and the OSM standard, and that will be your plugin for use. And what does it do? It loads base map. Okay. You come to here. You come to here, and you click on it. And after clicking on it, becomes part of a layer. We are going to do that together. Okay. So let's do that, and then we're going to go and see how you load data in QGIS. Okay. Okay. So we're going to load our plugins. You go to this web. Okay. You click on Quick Map Services, and then you click on OSM. You click on that. It gives you the map, base map. And then also it becomes one of the layer. It becomes a layer here. Okay. So for it to be shown here, it has to be checked here. If you unchecked it, it will disappear. Okay. So again, how do you load your plugin? You go to web, Quick Map Services, OSM, and you click on it. How do you get rid of it? You go to your layer, you right click, and remove it as a layer. Okay, let's exercise. I would like you to go load your plugin. After loading, I would like you to remove it. How did I do it? I went to Web, Quick Map Services, OSM, click on that, it becomes my layer. This is the layer base map here. But for me to see this base map, it has to be checked here in the E. If I uncheck it, it will disappear. If I check it, it will appear. How do I get rid of it? I right click, and then you can see here, remove layer. It asks if you want to remove, okay, it's gone. Okay, 2 minutes, let's do that. And if you're done, put one on the map. Load your plugin and check it so that you don't see it, and then remove it. Okay, let's go back to our slides. Okay, now we have covered how you get your plugin, covered how you can remove it. Now, the next, we're going to load data. How do we load data into QGIS? So QGIS has different type of files. Already seen that. You can use comma separated value. It can use raster. Can use vector. So I have two files that you've downloaded. One is comma separated value. That's what we're going to start with. And then one is a vector file. So for QGIS to work, your file has to contain a location, geographical information. Well, it has to contain latitude and longitude. If you don't have that, it'll be a problem. So it should contain location for the map. So how do you load our data? We're going to start with CSV file. So you load your data using layer. So you click on your layer, and then after that, it tells you to add a file. And then gives you all these file formats here, from vector, raster, but we're going to start with comma separated value file. And that one you use what? Delimited text layer, okay? So after clicking on that, again, you go to a layer, you add, we're going to start with the CSV file. We're going to use this, okay? Then you'll see a window like this, okay? And in this window, you see 3 dots. You see 3 dots here? You click on those 3 dots, and those 3 dots will give you access to your file. And you downloaded a file called country_co. And that's the file we're going to load, okay? So when you click on that, you take the file, and you have this file. If you downloaded it from the Google Drive, you should be having it in your data_science. You'll get this. You click on this, okay, and then it will the longitude and latitude, longitude goes to the X field, latitude to the Y field. And your data should have this, okay? And then the geometry CRS is this one here, okay? And then you click on add. After hitting on add, then you close. Then you will see something like these dots. Okay, something like this, the dots. And then on the left, the file you uploaded becomes a layer. Okay. Let me go back again. How do you load data in QGIS? You load data in QGIS using a layer. If you go to a layer, and this layer does very many things, but one of them is to add data to QGIS. You click on add layer, and there are very many different types of data format that can be used in QGIS. And the first one we're going to use is comma separated value. And to use comma separated value, you have to use eliminated text layer. Tomorrow or today depends on the time we're going to use vector because you're downloading two files. After that, there are three dots here. To click on those dots, you should be able to take you to your where you stored this data set that you downloaded. Okay. So when you click on that data set, you'll see a window like this. And this window, when your data has latitude, it will be on your Y, and where your data longitude will be on your X field. And then this will change to this. And then click on add and close. Then after closing, this data that you downloaded will become a layer. It will appear where the layer was. That's why I wanted us to have these layers here. And then you'll see dots. Okay. So let's do that. I'm going to give you 2 minutes. And then when you're done, just put one in the chat. Okay, so I'm going to go to my QGIS and we're going to do that together, okay? Okay, so we're going to load our data in QGIS, okay? To do that, we're going to go to layer. Look, you see my cursor? Layer. We're going to add layer. And we're going to add comma separated value, and we have to use add limited text, okay? So if I click on that, give me this window here. And this window has three dots, these three dots here. If I click on these three dots, it'll take you to where data underscore science, that's where I have my data. And so let me see if I have it here. Country. Let me see. I don't think I have it here. Country. country underscore. Yeah. See where my data is? Country underscore co.csv. And then if I open it, it will bring for me this. I have my longitude, X field, my latitude is here, and then I'll add, and then I close. And then I have all these dots. You might have different colors, but I have now my country underscore CO is a layer. Let's start again. Let me delete this layer here. Now we know how to delete the layer. You right click and remove it. Okay. Now I'm going to go to layer, add layer, add limited text with these three dots, data underscore science, and mine is down here. Open it. And then my longitude is in X field, latitude in Y field, and then my CRIS is this one here. And then what I'm going to do is I'm going to add it. Go back. There. Add layer. Add, close. Okay. So we have these dots here, and these dots represent, each dot is a country. Okay. But now we need to add a base map. That's now our plugin comes in. Okay. So we need to add a base map to this. So we now go to web, quick map service, OSM. Okay. So now I have two layers here. I have my data layer, I have my map layer. If I uncheck my data layer, all the data will disappear. If I want, I'll put it back. If I uncheck my map layer, the base map will disappear. Okay. So let's do that. And when you're done, 1 in the chat, then we move on from there. So are we okay up to getting the base map? If you're cool, let's just put 1 and then we go back and continue. So you got your data, and then you use the plugin to get the base map. Just type 1 when you're done. Okay. So I'm going to go back to the slide. So what do you do with what you have just brought in your QGIS? Okay. So the other things that you can do, one of them is attribute table. So this contains all the variables that are known as sets. So if you right click on the layer, you can open attribute table, and then you can also show that on the deck. It's like in ARA when you type view, this is what attribute table does, okay? You can also do editing. So if you right click on your layer, it will bring for you another window, sub window, and then you can do other things. So for us, we're going to work with the properties. You can do editing, okay? So you can also adjust the size of the labels. You can work with, you can do some classification, which we're going to do. You can adjust the size of markers. Okay, we're going to do that together. Okay. The thing that we also can do is called symbology. This symbology is for visualizing spatial data. So we're going to spend some time in this because this one is now where the descriptive analytics come in and prescriptive analytics come in, because you can do your predictive analytics, you save your data, and you bring it now in QGIS, and now help people make decisions. So this symbology is the one that's helped with that. So what does it do? So it defines how geographic features are visually represented on a map. You can change colors, you can change shape, you can change sizes. So how do you access it? You right click on your layer. When you right click on your layer, you go to symbology. And symbology has very, very many features. One of them is single symbol. If you use that, when you're using all features that the same style. For example, right now, we have our maps. I'm sure not all of us have the same color, but that's because the type of symbology that's being used is single symbol. You can also use categorical. So that one is based on category. For example, when you want to show the language types, another one is called graduated. This is based on numeric values. We're going to use all those. Another one is it's rule-based, and some are like heat map, okay? So we're going to spend some time playing with this symbology here, okay? And then after that, after playing with the symbology, then we're going to export our data. So how do you export your data? Use project. So if you click on your project, after getting what you're satisfied with, you go to export, and then you just export the data either in a map form or PDF and other format, okay? So before you go to prescriptive analytics, let's go and do some fun work with symbology, okay? Okay, so let me go back here. Okay, you're going to follow me, and then after I'm going to give you some exercise. So I'm going to go to my data, and this data is in where this layer. So to get to symbology, I right click on it. Okay. If I right click on that, I'll go to property. And this property has very, very many other things that you can do. But the only thing I need is symbology. If I click on this, you see the color of my map is kind of orange. And if you look at this, it's single symbol. I can change this color. So how do I do that? If I click down here, this is how I can change the color. So I can put it green, okay? And I click on OK. You see my color has changed to green. That's one thing I can do. I can go back. I go to properties. I can change the shape, okay? And if I click on OK, my shape, colors are changed. So that is being done in single symbol. So single symbol from our slide cover everything, okay? Another thing that I can do, I can go to graduated, okay? And then I can, from graduated, I can select another value here. Let's select something here. Okay, let me, what I can select. Let's just select Yale here. Okay. So I can, the color I can select different colors. Let me select like this one here. And then I can classify. See that? Oh, I need to change this. Let me go back to, yeah, it's much better. And then I also can see the histogram. Can load the values, can see the histogram here, okay? Click on OK. You can see here the range of the ranges here. You can see different colors. So if I check the rest, you can see only this has this. So we're going to do an exercise here. So what I would like you to do, I would like you to go to properties. You start with single symbol. I would like you to change the color of your, any color you want. I would like you to pick any shape you want. When you're done with that, we'd like you to go to graduated and pick, let me see what we can would like you to do here. What value? And do temperature and classify that. So if you classify temperature, also try to do histogram, okay? So I'm going to give you at least 5 minutes to do that. Okay? So let's do it. So let's do it in 5 minutes. Okay, type 1 when you're done in the chat. Okay. So I also would like to show you how you can also manipulate some of these icons here. So let me go back and change my go back and go back to single symbol. Okay. So you see these hands here where my cursor is? If you see my screen, just type 1 to make sure that you're seeing my screen. Okay, good. So if you see when I work when you open QGIS, it's these hands here, and that's you can just move these maps around. But sometimes when you want to increase the size of the map, you click on this plus here. You see that? And then when you want to reduce, you click on this minus here. But if you want to go back so that you can move these files, you move this map around, you have to go back and click on the hands. Okay? So let's go back to Uganda here. Okay, so if you want to zoom in Uganda and expand it, just go to this plus. And then now, if you want at least to move it around, you go back to that plus. I just wanted to show you that. Okay, that's one. And then you can also duplicate. You can also duplicate your layer. Okay. How do you do that? You go to layer. You know, this icon layer that's very many things. You can add data using layer, and also you can duplicate your layer. So I'm going to duplicate this layer. It gives you a name as a copy. I'm going to duplicate again. Okay. So now I'm going to rename the ones that are duplicated. So to rename it, just click on it. Sorry, go back here. If you click on it, you should be able to just type. Let's see here. Not mistaken here. If you click on it, you right click, it gives you a name. Okay. So I'm going to call this country _1. Okay. I'm going to call this, you right click and rename. I'm going to call it county _2. Okay. So you can do now things differently with each layer. Okay. So I just wanted to share this with you, that you can duplicate your layers. Okay. So what I'm going to do, I'm going to change. Okay. So this is what I'm going to do. I'm going to, for this layer country _1, I'm going to change the color to red. It's not red. Where's red? Okay. So you see now, the color of this layer is red. I'm going to change this to another color. Properties. Let's give it a blue. Okay. Okay, that's blue. Let me go back and reduce this to small so I can see other countries. Okay, so right now, if I uncheck this and check this, I have only this layer here. If I check that, the base map is gone. Okay. If I uncheck the other two, I have only blue. So when you're doing some analysis, you can work with each layer independently. Okay. So, for example, what I can do, I can go here, and then I go to graduated. I go to average temperature. I classify the gram load value. So this is my temperature. Okay. And then I can go to this one. I can do yield. The value is yield. Classify, load, and so forth. So I wanted to share that with you. Okay. So I just want to introduce QGIS today. Tomorrow, I will show you the descriptive analytics of how to apply QGIS, and then we'll finish with RShiny. Okay. So today we introduce QGIS for the prescriptive analytics. I've done some analysis with predictive analytics with different methods and save the results in raster form, and vector form. So both raster and vector form. So one of the files that you have tomorrow will show you how now you can apply what you've been doing in predictive analytics to make a decision. So it's coming now to 5. Thank you very much. I can get you back to David. David, back to you.
Thank you very much, Stephen and Peace, for yet another educative webinar. I think we don't have any housekeeping today. I think we can just close and meet again tomorrow to wind up the week. Thank you very much, everyone. Thank you to the participants. See you again tomorrow.